Hello everyone, I am.
And my name is Cody Hatfield.
So today I and Cody are showing the work called Optimization Layers in Neural Network Architecture. And this work was published in ICML 2017. And we're going to explain the contents of this paper, and also we have done some additional experiments, so we're going to show those results as well. So here's our outline for the talk. So first of all, I'm going to explain some basic concept used in this paper in the introduction, and I will explain the method, which is the OptNet, and then they proposed the solver as well to train the OptNet based neural network.
We will then describe some additional properties of OptNet, at which point we'll launch right into some case studies that the authors present to support some of their claims. Then, we'll discuss some limitations of the paper, as well as some brief quibbles with its presentation, before launching into an experiment we ran using OptNet to predict magnetic fields. We'll go over the results of our experiment, and then draw some conclusions about what we've seen today, and finally do a little question and answer session at the end to address any concerns or curiosities that anyone might be having. For this presentation, we will primarily make references to these two papers. The first is the original paper on OptNet, which shall be our primary focus. The second provides a methodology that Source 1 uses to parallelize its operations. OptNet is currently programmed in Python and requires some prerequisite libraries. As per most machine learning applications, NumPy will be required. Now, the authors worked very closely with the creators of Pytorch and developed an OptNet implementation that can be added to Pytorch models like any other layer, thus allowing OptNet models to be trained using the same code one might use to train a neural network. We used this Pytorch implementation in our exploration of OptNet, and so we've gone ahead and listed it here. Matplotlib is also required for the example training code provided by the authors. Qtph is a library created by the authors which contains the OptNet Pytorch implementation. This library can be installed via pip. The final library is not required for OptNet. It is used in our later experiments with magnetic fields, where we use the Python library magpylib to generate our learning data. Thus, this library is optional, and only required if you wish to generate additional training data for our experiment, which was unrelated to the paper.
So as an introduction, let me talk about neural network. I'm pretty sure many students in this course have learned a neural network. So just as a reminder, it minimizes a loss function over a set of data, and it can approximate any arbitrary distribution given enough epochs and data and layers in the network structures. It's normally difficult to guarantee convergence to global optimum, and also weights and biases can be learned from data. Meanwhile, on the left-hand side of the slide, so this is another key concept in this paper, which is quadratic optimization. We have learned many times in this course. So it minimizes quadratic functions such that solution found must fall within given linear constraints. And it's limited to certain problem spaces, but it is incredibly powerful and well researched in many areas. And functions and constraints can be learned from data. And then application is a lot again. So for example, finances and machine learning. We have learned SVM in the machine learning course, and also there are applications in control theories. So here are some approaches in optimization in neural networks. So approach 1 is unrolling. So for example, gradient descent. So unrolling obtain derivatives during training and incorporate these derivatives in the loop optimization procedures. Unrolling typically requires a substantially larger network, which also means that it requires even more computational complexity. And approach 2 is to directly differentiate through augment. And this paper follows this approach too. What kind of augment? So specifically, this paper focuses on quadratic optimizations. So OptNet. So this paper introduces a formulation that allows for quadratic optimization programs to be added as layers into a neural network. So once they are added, the entire model can be trained at once. So in the illustration on the right hand side, you can see that optimization program is inserted as one of the layers. According to this paper, ideally this means that the optimization framework can reduce the depth of the network while also keeping a rich representation by the network. And furthermore, these optimization layers can receive a high degree of tuning. This allows for embedding prior knowledge into the network in the form of setting constraints or functions. All the terms of the optimization program can be function of ZI, which is the output of previous layer, so long as they are differentiable. And as we will explain in detail in the following slide, this paper derives the gradients by taking matrix differential of the KKT condition of the optimization program as its solutions. Let's take a close look at the proposed model. OptLayer can be any optimization program, and in this paper they study OptNet layers defined by a quadratic program, and output of the I+1 layer in network is the solution to a constraint optimization program based on previous layer. And then, as is well known, this problem can be solved in polynomial time using a variety of methods. And one of the state-of-the-art is primal dual interior point method, which will be also used in the solver proposed in this paper. And as you can see, so here are some notification in the optimization formulation. So ZI is the output of the previous layer, which is optimization variable. And second bullet on the slide lists up the parameters used in the formulation. So they all depend in any differentiable way on the previous layer ZI. And these layers can be learned by taking the gradients of some loss function with regard to these parameters. And again, the optimal solution of these optimization problems become the output of the layer. And the fourth pass in the OptNet architecture involves simply setting up and finding the solution to this optimization problem. Training deep architecture, however, requires that we not just have a forward pass in our network, but also a backward pass. And this requires that we compute the derivatives of the solution to the quadratic programming with respect to its input parameters. To obtain these variables, they differentiate the KKT condition of the optimization program as a solution to the problem using technique from matrix differential calculus. The Lagrangian of optimization program is given as in the slide at the top, where we are the dual variable on the equality constraints, and lambda are the dual variable on the inequality constraint. The KKT conditions for optimality are also shown in the middle part of the slide, where D creates a diagonal matrix from a vector, and Z star, V star, and lambda star are the optimal primal and dual variables. And finally, taking the differential of this condition and some manipulation finds necessary gradients for back propagation as in the bottom of the slide. And we would like to just also add that there could be different ways a layer can be configured before training begins. So this slide shows two ways of different configurations. So first way is on the left hand side of the slide, where ZY, Z2, Z3 are components of the optimized output Z, also known as ZI+1, and ZI is the output from the previous layer again. So A is a constant matrix and it doesn't change. B is constant in first and third components, but is functionally dependent on ZI for its second component. Right hand side shows the second way of configuration. So B is a linear network which transforms ZI into some future space, while A remains constant. The B neural network is trained to transform ZI vectors into B constraints that feasibly match the training data. And ZI and Z don't need to have the same dimensions. And next, let me explain their batch-parallelized solver. Deep neural networks are typically trained in mini batches to take advantage of efficient data parallel GPU operations. Without mini batching on the GPU, many modern deep learning architectures become intractable for all practical purposes. However, today's state-of-the-art QP solver like Groby and CPLEX do not have the capability of solving multiple optimization problems on a GPU in parallel across the entire mini batch. This makes larger OptNet layers become quickly intractable compared to a fully connected layers with the same number of parameters. To overcome this performance bottleneck in OptNet, this paper implemented a GPU-based primordial interior point method based on the reference to. The performance experiments shown on the right top in the slide shows that their solver is significantly faster than the standard non-batch solver Groby in larger batch size. An interesting quirk of this implementation is that it computes the gradients required for the backward pass whenever the QP is solved. And this gives tremendous saving time. Here are some mathematical properties of OptNet layers. So first property is Opto layers are self-differentiable everywhere and differentiable over a measure zero set of points. And the next two properties show the representational power of the OptNet layer, specifically how OptNet layer compares to the common linear layer followed by a ReLU activations. So the second property is OptNet can approximate arbitrary element-wise piecewise linear functions and thus can represent a ReLU layer. And third property is that there are functions represented by OptNet layer which cannot be represented exactly by a two-layer ReLU layer. Their next experiment studies how we can use the OptNet architecture to improve upon signal processing technique that currently uses convex optimization as a basis. Specifically, their goal in this case is to denoise a noisy one-dimensional signal given training data, consistency of noisy and clean signals generated from the same distributions. Their baseline is the total variational denoising, TVD, which is a particularly common and simple approach in the task. And this is a denoising method which attempts to remove noise from a signal while still preserving hard changes in the signal. And this contrasts with other denoising methods like linear smoothing. Many other methods do reduce noise, but they also blur these hard edges, thus losing some information. Specifically, the total variation denoising approach attempts to smooth some noisy observed signal Y by solving the optimization problem as in the left top of the slide, where Y is the true signal, Z is the predicted signal, lambda is a regularizer, and D is the first order differencing operator. table on the right top on the slide shows the error rate of these 4 approaches. The table tells that first, a fully connected neural network performs substantially worse on this denoising task compared to the convex optimization program. Pure OptNet, where all parameters are learned, is outperformed by a fully connected network. Interestingly, the pure OptNet method learned a D matrix that very closely aligns with what the total variation method uses. Finally, OptNet, which is tuned such that the constraint is initialized to the first order differentiation constraints D from the total variation method, in turn outperforms the total variation method.
The fact that OptNet learned the differencing operator from the data is really quite interesting, as it speaks to OptNet's ability to learn hard rules and relationships from training data. Furthermore, this also demonstrates that OptNet's learned parameters are very interpretable. We can directly look at the learned values for the differencing operator and see for ourselves that they closely align with the traditional differencing operator that the total variation method uses. The next case study involves a miniaturized version of Sudoku. As a reminder, Sudoku is a classic logic game which involves filling in missing integers of a grid. However, one cannot place any integer anywhere they want. There are rules that must be followed. Each integer must inclusively be between 1 and the width of the board, and each row and each column of the board must include 1 and only 1 of each possible integer. The goal is to fill out the entire board such that the aforementioned rules are followed in the final composition. The problem of solving a Sudoku board is trivial and incredibly easy for linear programs, so long as the linear program knows the rule of the game. However, neural network architectures have great difficulty when applied to this problem space. It is often notoriously difficult to encode prior knowledge into neural networks, aside from reusing previously trained weights and biases. Therefore, networks must learn the rules of Sudoku simply by observing input and output data. Furthermore, the paper points out that neural networks have difficulty learning hard constraints, which therefore makes it even more difficult for them to learn how to solve Sudoku puzzles, as the rules of Sudoku are rigid and inflexible. Thus, the paper wishes to demonstrate OptNet's ability to operate in a problem space that neural networks have great difficulty in, by learning the rules and then accurately solving these Sudoku board puzzles. Now, I would like to comment on a few details regarding how the paper approaches this problem. Firstly, the paper uses a mini Sudoku board instead of a full Sudoku board. A full Sudoku puzzle involves a 9x9 grid, which is composed of separate 3x3 grids that have additional rules that must be followed. Thus, this problem is simpler than a full Sudoku puzzle. Secondly, the paper uses a one-hot encoding for the possible integer values placed on the board. Because the mini Sudoku board is 4x4, the range of valid integers is between 1 and 4, and therefore there are 4 different one-hot encodings for each possible integer, where the 0 vector is the encoding used for an unknown or unfilled space. Thus, the total problem space of this problem is a 3-dimensional binary matrix with size 4x4x4. Now let us break down how the author structured a single OptNet layer so that it can try to learn how to solve the mini Sudoku problem. OptNet follows the standard form of quadratic programming, which you can see displayed at the top of the slide. An OptNet layer receives as input some vector zi, and generates an output vector z, which attempts to solve the quadratic programming problem. Zi can be passed to functions that generate the so-called constant terms of the quadratic optimization problem, so long as these functions are differentiable and they depend on Zi in some differentiable way, or they are truly constant regardless of Zi, then this layer can be trained using the Pytorch library on a given set of data. However, both zi and z are expected to be vectors in a quadratic problem standard form. Thus, the input passed into this layer must be flattened, and the output returned from this layer reshaped to match the dimensionality of the Sudoku problem space. However, these are trivial tasks for the Pytorch library, and this fact is only mentioned as a simple clarification. Now, the authors of the paper engaged in a substantial amount of tuning of the OptNet layer parameters, which I have briefly described on this page. Big Q is initialized to an identity matrix. This matrix is untrainable. That is, its value remains constant for all data points across all epochs, and it is not modified during the training process. Big Q is also multiplied by some scalar constant called the Q penalty when it is initialized, and the primary purpose of this constraint is to serve as a regularizer that encourages small component values of z. Little q is simply the original board vector zi that is passed as input into the layer. This vector is not trainable either, due to it not having any numerical parameters to learn. G is a constant identity matrix, which has been multiplied by -1, whereas H is a constant 0 vector. These two constraints enforce the requirement that all values entered onto the board must be greater than 0. A is a trainable matrix, and all of its components are randomly initialized. B is interesting, because it is not a trainable parameter, but it is not constant either. Rather, there is another vector called z0, and it is this z0 vector which is trainable. During each iteration, the component-wise natural log of z0 is taken, and this natural log of the z0 vector multiplies the current matrix A, and the new vector which results from this operation is passed to the OptNet layer as the B value. I am not totally sure why the author structured this constraint in this way, but my guess is that it ensures that the B value passed to the quadratic programming solver is always some linear combination of the matrix A, while taking the log of z0 helps the derivatives of the constraints maintain some useful, as of yet undetermined property. To compare performance, the authors constructed a convolutional neural network to see how well their tuned OptNet layer fared against this so-called traditional machine learning structure. We can see results of this in the right column of the slide, where the red and peach lines correspond to the convolutional network, while the blue and aqua lines correspond to the performance of OptNet. The red line in the first graph corresponds to the convolutional network during training, and it rather quickly begins to memorize the data as the training loss converges towards 0. Despite this apparent success, however, one can examine the convolutional network's testing loss and see that it performs about the same as OptNet's loss values. Interestingly, the training and testing loss for OptNet are closely aligned and do not diverge from each other. Both of their losses do decrease with time, which implies that OptNet is indeed learning something useful, but I cannot definitively answer why this is happening without more exploration. The true power of OptNet is revealed, however, when we compare the accuracies between it and the convolutional network. Despite the convolutional network getting a substantially lower training loss than OptNet, the convolutional network performs substantially worse in the accuracy metric than OptNet does. In fact, the testing accuracy of OptNet is almost 2 full magnitudes smaller than the testing accuracy of the convolutional neural network, despite the fact that the convolutional neural network has far more weights and biases, and thus, theoretically, more expressive power. This speaks to the idea that OptNet is able to more efficiently learn some kinds of problems, although this would need to be investigated further in order to formulate any kinds of guarantees on this matter. Now, the paper states in its abstract that OptNet is capable of learning to play Sudoku while just being given the input puzzles and output solutions, with no a priori information about the rules of the game. The results of the Sudoku case study appear to support this claim, with the trained A matrix and Z0 vector calculating the correct solution to the overwhelming majority of the Sudoku puzzles given as test input. Interestingly, OptNet's loss and accuracy metrics appear to follow a pattern of rising and falling, wherein the performance of these metrics gets worse for a period of time before sharply dropping, and then repeating the process. I am not sure why this happens, but it is a pattern that played out in our own experiments as well. Thus far, we have mostly talked about promising behavior exhibited by OptNet and its various properties when applied to interesting problem domains. However, there are some slight criticisms to be made about OptNet, as well as how this paper presents its findings. Now, before I begin, I would like to reiterate that I find OptNet to be an exciting development in machine learning, as it offers a new and quite powerful learning structure that goes beyond what I feel is the widespread practice in our field of blindly throwing data at neural networks and hoping that they do something interesting. But I would not be a future scientist if I did not attempt to poke holes in and take quibbles with the research of others, and this situation is no different. Firstly, I would like to point out that the case studies offered by the authors required substantial tuning of a single OptNet layer in order for OptNet to reach adequate performance. The authors briefly mentioned the necessity of tuning in section 3.3 of the paper, however, I feel like it was not emphasized nor expanded upon enough. This extensive ability to tune and configure OptNet does indeed appear to be a sort of double-edged sword, where extensive tuning can cause developing with OptNet to straddle the line between machine learning and simple manual formulation of a quadratic optimization problem. Such necessity of tuning is first exemplified by the denoising example. OptNet could not compete with the traditional total variational method unless a priori knowledge regarding the difference operator was encoded into the layer. This trend is further demonstrated with the Sudoku case study. Let us recall that the authors stated that OptNet learned the rules of Sudoku without any a priori knowledge of its rules. I take issue with this statement, because after personally examining the code provided by the authors, I am left with no choice but to conclude that a priori knowledge was indeed given to OptNet, although not in ways that are immediately obvious. This prior knowledge was encoded through the G, H, and Q constraints of the tuned OptNet layer, where they interacted with the very structure of the quadratic programming problem to essentially induce the embedded knowledge into the learning process. For starters, consider that G and H apply a hard constraint that ensures all integers generated to solve the problem are greater than 0. While this rule might seem trivial, it is of tantamount importance for the Sudoku problem space. Recall that Sudoku requires all of the rows and all of the columns to have exactly one of each possible integer in them. This rule is quite hard to encode in a single constraint, but it is possible when one considers the interactions of all the constraints in this problem space. To further prove this, let us examine the Q matrix, which on its surface appears to simply encourage finding a solution Z with small magnitude. This is not solely the case, however, as Q also serves an additional purpose of encoding a soft constraint on the maximum value of the Z components. Now we can reinterpret the column-row rule of Sudoku as one in which the sum of components in each row and each column all equal the same number, where the values of the components are restricted to some range. Thus, our trainable A and Z not parameters learn to approximate this new rule of summation for the rows and columns, while our G and H constraints ensure that all values are greater than 0. Finally, because the Q component encourages small component values in the solution, it in turn pressures the chosen Z to not go beyond the maximum allowed value. Now, I would go so far as to posit that had OptNet in its current form simply tried to learn all of the parameters by itself without being given this prior knowledge, it would have utterly failed to learn the rules of Sudoku without some additional mechanism to aid it. All of this speaks to the fact that the current incarnation of OptNet only performs well when it is operating in some problem space that can incorporate or be formulated as quadratic programming in some capacity. Thus, we have come up with the following postulates regarding the effectiveness of OptNet in various problem domains. First, OptNet layers will dramatically reduce the number of layers for networks operating in problem spaces that are represented as a quadratic optimization problem. Second, OptNet layers will have a diminished effect on problem spaces that are partially represented as a quadratic optimization problem. Third, OptNet layers will have no effect, or possibly even an opposite effect, for problem spaces that are not represented as a quadratic optimization problem. We presently have no immediate and definitive proof of these postulates, but they feel like entirely reasonable avenues to explore for future research that could be quite promising. I, for one, would be very interested to see a line of inquiry around what it actually means to be fully versus partially represented as a quadratic optimization problem. While some of these may seem a bit trivial at first, but they do tell us something deeply important about OptNet's capabilities when embedded into deep learning architectures. The paper's primary focus was on attempting to show OptNet's ability to dramatically reduce the number of layers needed to learn a problem space. Thus, all of the case studies have involved a single OptNet layer and comparing its performance against a deep learning network. While these cases have demonstrated evidence supporting the author's claims, we feel that OptNet has a large variety of implementations, and thus decided to explore in a new direction. One very promising possibility is that of embedding OptNet into a larger deep learning network. You may recall from the previous slide that we claimed our three postulates hold significance in such a scenario. Among their many versatile uses as function approximators and high-dimensional linear separators, neural networks are also adept at transforming arbitrary numerical spaces into other numerical spaces, even if the starting space has a different dimensionality than the ending space. Therefore, by setting a forest of neural networks to feed their outputs into an OptNet layer, we hypothesize that the neural networks can learn to transform the raw data into a space that is at least partially formulated as a quadratic optimization problem. If our postulates hold true, then OptNet will reduce the number of layers needed to learn the problem space. This effect may be diminished under postulate 2, but this diminishment might not be unacceptably awful. Given how often our field celebrates imperfect neural networks, even a reduced effectiveness may be worthwhile in certain problem domains. Thus, we needed to find an example that was sufficiently complex, such that we could attempt to push the representational power of these tools as far as possible. Particular care was taken to choose a problem domain which was complex enough such that a deep learning-powered transformational network was required, but also simple enough that it was both tractable and such that training data could be easily acquired. With the previous requirements in mind, a seemingly simple problem of generating magnetic fields was chosen. Magnetic fields exhibit nonlinearity, especially when calculating the field strength at a particular point in space. The relationship between magnetic field strength and the position of the magnet has many factors, including distance to the magnet, the strength of the magnet, orientation to the magnet, and taking an integral over the space occupied by the magnet. Thus, this represents a rich problem space to learn for OptNet. The training data was created using the magpylib library for Python. This library has an enormous set of features for generating magnetic fields, and was invaluable in this experiment. Each point of training data is created by placing a bar magnet at various locations around the world space. This world space is a 20 by 20 matrix, where each component of the matrix is a two-dimensional vector. A 20 by 20 grid of positions is sampled from the world space, and the values from these samples comprise our training and testing data. For all samples and all data points in both datasets, the strength, size, and shape of the magnet is kept constant. You can see in the right column an example magnetic field which was generated using magpylib. The actual volume of the magnet is not shown, but its center is marked with the blue circle. Only 500 data points were created for both train and test datasets, due to time constraints both on data generation as well as the training process itself. The magnetic field you see in the right column is actually the output, or target data, that OptNet is trying to learn to predict. The input data is another 20 by 20 grid, where each component is a two-dimensional vector. Only instead of holding the strength of the magnetic field at that position, the input matrices positions instead contains the vector whose magnitude is the distance from the position to the center of the magnet, and the vector points towards the center of the magnet. While formulating the input data into a different structure might have improved generation performance, the goal of this experiment was to try and train neural networks to learn a transformation of the input data such that the data is formulated into a problem space that is more conducive for quadratic optimization. Now, for the quadratic problem shown at the top of the slide, we needed to create a neural network to feed into each of its parameters. Thus, a very simple quadratic transformer model is created and initialized to random weights. Each parameter of the quadratic optimization problem receives its own individual copy of a quadratic transformer, whose weights and biases are separate from the transformers used by other parameters. The input of each transformer is a vector created by flattening the distance field, which is immediately fed into a linear layer which has the same size of the input. This linear layer feeds into an ELU layer, where ELU is very similar to ReLU, except it is smooth and continuously differentiable everywhere. This ELU feeds into two more sequential linear layers before passing through another ELU and then through another linear layer. 4 linear layers and 2 ELU layers felt sufficiently adequate enough to capture nonlinearity in the transformation process. At the final step, the data is passed into another linear layer, whose output size is set to whatever the necessary size is for the OptNet parameter that the network is feeding into. For example, big Q and little q need to have their dimensions closely aligned with the dimensions of z, but A and B are free to take on heights of whatever they wish. Thus, for the current deep OptNet model used in this experiment, A, B, G, and H all have a height of 50, which effectively allows them to encode up to 50 hard constraints. To compare against traditional neural network methods, a fully connected model was created and trained on the same dataset as OptNet. This model takes as input the distance field, and returns as output its prediction for the magnetic field. The layers of this fully connected model follow a very simple pattern. The input feeds into a linear layer, which has a size of 256 nodes. This then feeds into another linear layer of size 256, which finally itself feeds into an ELU layer. This pattern is repeated until there are 10 total linear layers in the model and 5 total ELU layers. Some tuning and experimentation was done to try and find an architecture that gives good generalization and good performance, and the one described here gave the best results out of all those that were tried. Here we can see the results of applying our trained models onto test data, which they have not seen before. The index number at the top gives the index of the test data point used for the shown rendering. The left image shows the original magnetic field that we are trying to generate, while the middle and the right show the predictions of deep OptNet and our deep fully connected neural network, respectively. We can see that both deep OptNet and deep FC correctly capture the basic shape and magnitude of the magnetic field near the magnet. However, the predictions grow more inaccurate the further from the magnet a position becomes. Now, in contrast to the Sudoku puzzle, there wasn't a great way to measure an accuracy metric for this problem space, and thus a mean-squared error loss is the only numerical metric available to objectively judge performance. And yet, a visual examination with the naked eye would lead most people to conclude that Deep OptNet generated a far better prediction than Deep FC. The reason for the Deep Fully Connected Network receiving a lower MSE score than Deep OptNet is not definitively known at this time, but the current hypothesis is that the Deep FC network is pursuing a strategy that I call blurring, wherein the neural network attempts to essentially split the difference between the global minima and maxima of the training data. Thus, while the structure of the field generated by the FC network is worse than the one generated by Deep OptNet, its average difference from the ground truth is likely much lower, for by pursuing an average value, the Deep FC model ensures that most of its components are not far off from the ground truth components. While I do not presently have proof of this claim, this is an effect I have seen play out with many other neural networks that I have trained over the years. This lends evidence to the idea that OptNet is potentially better at generalizing than a traditional neural network. This improved ability to generalize to unseen data is not without a cost, however, as both models were run on the same dataset for 600 epochs, and yet Deep OptNet took substantially longer to complete its training. In comparison, the fully connected neural network model required only a few minutes to train, while the OptNet model took around 4 hours. Thus, while the parallelization of the quadratic programming solver certainly improves performance, it unfortunately still cannot keep up with a fully connected neural network in terms of training time. This begs the question of if the fully connected network was trained for the same amount of time rather than the same amount of epochs as the OptNet model, perhaps it might give an equivalent if not better performance to OptNet. Nonetheless, these results do provide more evidence to the idea that OptNet is capable of providing better results with less layers than a fully connected neural network. Here is a second rendering from the test dataset, this time using index 224. We see the loss of accuracy as distance increases from the magnet more clearly in this example. Deep OptNet still appears to have visually created a better prediction, and the fact that Deep FC is still setting the magnitudes of the field vectors to an intensity of light green, despite being so far away from the magnet, lends further credence to the blurring hypothesis. Compare this to the original example, and even the Deep OptNet prediction, where the vectors start to become more purple and with less intensity as they move further and further away from the magnet center. In conclusion, we have introduced and explored OptNet, which is a batch-parallelizable quadratic programming solver that integrates with the Pytorch library, such that it can be trained like any traditional neural network. OptNet provides a new tool for machine learning engineers to tackle problems with, particularly for some problem spaces that are resistant to neural network training but can be represented in some way as a quadratic programming problem. OptNet is highly configurable, but we have seen that this is not always a good thing. Thus, care should be taken when using OptNet to ensure that the tuning one uses is appropriate and not detrimental. The paper also demonstrates evidence that OptNet can reduce the number of layers needed to train a network. However, we postulate that this benefit is limited only to certain problem spaces. From our simple magnetic field experiments, OptNet does show promising results when embedded into deep learning architecture. More robust explorations of OptNet are likely required, including a potential search for some mechanism that will allow OptNet to truly learn all of its parameters for the Sudoku problem without any prior knowledge encoded. If you're so inclined, you can download the link for our magnetic field experiments using the link that's on the screen. At the very least, I hope that this link gives some good example code for you to follow as you begin exploring OptNet yourself. I would like to add a small caveat to this, however. Due to the sheer size of some of the model files generated by OptNet, I was not able to successfully upload them to GitHub. Thus, if you do download these files, you will need to retrain the model yourself. There are instructions to do so on the GitHub page. Thus, at this point, I would like to open up the floor to our question and answer session, where we will do our best to try and answer any inquiries you might have about our process or about OptNet in general.